Welcome to the deep dive. Today, our mission is to extract some, universal lessons in system design and problem solving.
From what is honestly a really specific source.
Yeah, super specific. We're looking at a developer's technical notes, specifically part 95 of a series focused on programming in Haskell.
Right.
And this entire entry is dedicated to optimizing a Chinese numeral parser.
Which I know sounds completely niche.
Yeah, a technical log about Haskell parsing sounds incredibly dry,
Yeah.
but here's why you should care.
Totally.
Usually we think about writing software as this pure logic exercise.
Yeah.
Like engineering a steel bridge.
Right. You stack the mathematical bricks of code.
Exactly. The computer reads them perfectly, and the structural integrity just holds. It's clean, it's predictable.
But then you build a tool to parse human language.
Right. And you are suddenly stepping completely away from that pristine universe.
You really are. It becomes this fascinating collision between the rigid binary rules of computer science and the incredibly unpredictable, messy nature of human expression.
And culture.
Yeah, and culture. And what's brilliant about this particular log is how it captures that exact collision. These hyper-specific technical notes, they so often hide profound universal lessons, about how we handle scale, how we organize our workspaces, and
how we adapt those rigid systems to human quirks.
Exactly.
And that is exactly what we're exploring today. We're going to look really closely at this programming challenge to pull out 3 nuggets of knowledge for you.
3 big takeaways.
Right. We will learn how to cleanly organize complex systems. We will uncover a centuries-old anti-fraud mechanism hiding in plain sight. And we will get a masterclass in algorithmic efficiency.
Sounds like a lot for one Haskell parser.
It is. Okay, let's unpack this. We have to begin at the foundation.
Yeah.
Before we even look at what this code is actually doing.
And the numbers it's trying to read.
Right. Before any of that,
Yeah.
we need to look at how the developer chose to structure the code itself.
The architecture of the workspace, essentially.
Yeah.
Because when you are writing software, especially in a functional programming language like Haskell, where you put your logic is honestly just as important as what the logic does.
Right. And the very first change the developer outlines in their notes is all about encapsulation.
Encapsulation, yes.
They took a specific function, a piece of code called is Chinese numeral or digit, and they moved it completely out of the global scope.
Right.
And instead, they tucked it neatly away into a local where clause inside a larger parent function called pchapter.
Now, for those of you who don't write code every day, let's just talk about what global scope actually means in practice.
Yeah, let's break that down.
So in programming, the global scope means a variable or a function is accessible from absolutely anywhere in the program.
It's just out in the open.
Exactly. Any other piece of code can see it, it can call it, or potentially, trip over it.
Right.
But when a developer moves a function into a where clause, they are making it local. It only exists and can only be used within the specific boundaries of that parent function.
So imagine a massive, chaotic, shared house kitchen.
Oh, I've lived in a few of those.
Right. The global scope is essentially leaving every single one of your highly specialized utensils out on the main counter.
It's just scattered everywhere.
Yeah. You have your garlic press, your melon baller, your specific avocado slicer just sitting out in the open.
And if everyone in the house is doing that,
the counter is completely unusable. The developer notes explicitly refer to this as preventing namespace pollution.
Namespace pollution, yeah.
The counter is so cluttered with specialized tools that you can't even, make a simple sandwich without knocking over a pasta maker.
That is a perfect way to visualize it, because when the developer takes that as Chinese numeral or digit function and puts it into a where clause,
right,
it's like they took that highly specialized melon baller and put it into a private, clearly labeled drawer.
I love that.
It's still right there when the pchapter function needs it to, prep a meal.
But it's no longer cluttering up the communal kitchen counter for the rest of the program.
Exactly. It keeps the logic tucked neatly exactly where it belongs.
But wait, hold on.
Yeah.
I mean, I see the value in organizing the kitchen, obviously. But doesn't this create a totally different problem?
How you mean?
Well, if you hide the melon baller in a locked drawer, how do you know it's not broken? In standard software development, aren't you supposed to test every single function directly to make sure it works?
This raises an important question, and it is the exact trade-off the developer wrestles with in the notes.
Right, because you can't see it anymore.
You were talking about testability. You generally want automated tests for every tiny piece of logic.
Yeah.
But if a function is tucked away in a local where clause, it is entirely hidden from the outside world.
Right.
Your testing framework cannot reach into that private drawer to check if the tool is sharp. You have deliberately walled it off.
So by cleaning up the workspace, you've accidentally made it impossible for the health inspector to check your tools.
That's one way to look at it, yeah.
So how do you resolve that without just throwing all the tools back on the counter?
You take a really pragmatic approach. The developer states in the logs that we can always just test against pchapter instead.
The parent function.
Exactly. They are arguing that we don't need to test the hidden microscopic function directly. We just test the parent.
Right, because it uses the smaller function.
Think about it. If pchapter consistently and successfully parses a chapter number from a text, we know with absolute certainty that the hidden is Chinese numeral or digit tool inside of it must be working perfectly.
Okay, yeah, that makes a lot of sense.
Right.
It's choosing practical results over, like, dogmatic rule following.
Exactly.
The rigid rulebook says you have to test everything directly. But the developer recognizes that a clean, unpolluted workspace is ultimately more valuable.
You can still ensure quality by checking the final output of the machine rather than obsessing over every single internal gear.
It's a great reminder for anyone designing a workflow, honestly, even outside of software.
Oh, absolutely.
You don't always need to micromanage and measure every single tiny subtask if the primary system is producing the correct verified result.
You can trust that the encapsulated processes are doing their job.
Totally. So, okay, we built this pristine, organized, isolated little box for our code to live in.
Nice and tidy.
But a parser is only as good as the messy human data you feed into it.
Oh, here we go.
And this is where the log transitions from the structure of the workspace to the actual text it's trying to read.
Right.
When this developer opened the door to parsing Chinese numerals, they didn't just find standard number.
No, they did not.
They collided with a 600-year-old security protocol.
The data itself introduces an entirely new historical layer of complexity.
Yeah.
The developer notes that they had to update the parsing rules to include something called big writing.
Big writing.
Yeah. In Pinyin, that's pronounced dashi.
And to be clear for you listening, this isn't just like a slight variation in font or making the text bold. This is a completely distinct, highly formal numeral system. If you picture the standard Chinese character for the number 1.
Yeah, it's just a single horizontal stroke.
Exactly. It's incredibly minimalist, just one line.
Yep.
But the big writing version of the number 1 is an architectural stack of about 12 distinct strokes.
It looks less like a number and more like an intricate drawing.
Right. It has massive visual density.
And that visual complexity is the entire point. There is a very specific historical reason for that density, and it has absolutely nothing to do with mathematics.
Here's where it gets really interesting. If you are a software engineer building a tool to parse chapter numbers in typical novels.
Which is the stated goal of this project.
Right. Why on earth are you programming it to understand these massive, complex characters? Chapters are usually just chapter 1, chapter 2.
Yeah.
Why add this highly specific, visually overwhelming system to your code?
Well, it all comes down to the original purpose of the big writing system. This is an anti-fraud mechanism. Dashi was designed specifically for financial and legal contexts. We are talking about banking documents, accounting ledgers, and writing checks to prevent fraud.
It's analog cryptography.
That is exactly what it is. Let's go back to that standard numeral for the number 1, that single horizontal line.
Okay, the simple one.
Right. Imagine a merchant in ancient China keeping a ledger. If they write down that someone owes them 1,000 coins, and the 1 is just a simple stroke.
Oh, I see where this is going.
A fraudster could easily take a brush, add a single vertical stroke to that line, and completely change its value to a 10.
Wow.
The document is fundamentally altered with barely any effort.
So you invent numbers that are impossible to alter.
Precisely. The big writing characters are deliberately engineered to be so intricate, so packed with overlapping strokes, that you cannot add ink to them without making it blatantly obvious that the document has been tampered with.
Because there's no room to hide a new stroke.
Right. You can't turn a 12-stroke, highly specific character into a different number just by adding a line. They're tamper-proof numbers.
Okay, I love the history, but I have to push back here.
Sure.
That still leaves my core question unanswered.
Which is?
Why is a high-security banking script showing up in a software tool designed to read chapter headings in fiction novels?
Yes.
If you are building a parser for books, shouldn't you just expect standard numbers? Why not just build the system for the standard inputs?
Because software has to serve human beings, and human beings are wonderfully unpredictable.
That is very true.
The developer explicitly notes this reality in the text. While you certainly don't see Dashi every day in a typical novel, they notice that some authors actually choose to use these formal, complex numerals for their chapter numbers anyway.
Wait, really? Just for the aesthetic?
Yes. Maybe the author wants the novel to feel archaic or highly formal.
Oh, like a historical drama.
Exactly. Or maybe they just like the visual weight of those dense characters sitting at the top of the page. The point is, the technical system, the parser, has to account for this artistic choice.
That's wild.
It perfectly highlights how cultural data systems bleed into unexpected places.
Yeah.
A tool designed centuries ago for cold, hard banking security is repurposed by a modern artist for literary flair. And suddenly, a software engineer has to write extra logic to understand it.
It really shows you that when you build systems for human inputs, you cannot just build for the logical ideal.
You really can't.
You can't demand that the user conforms to your rigid expectations. You have to build for the messy, creative reality. You have to be incredibly adaptable.
But here is the catch. That adaptability always comes with a cost.
Right.
And that brings us perfectly to the next major technical challenge the developer faced in the logs.
The need for speed. Because by expanding this parser to include all these complex, dense, big writing characters, along with all the standard numerals and their variants, the program now has a much, much larger checklist of characters it needs to cross-reference every single time it reads a word.
The computational load increases significantly. You have asked the machine to look for a lot more things.
Right. And if you aren't careful, expanding that checklist could slow the whole system down to an absolute crawl.
Right.
The computer has to work harder for every single character it encounters. So how does the developer ensure this doesn't happen?
This is a great transition.
This is our third nugget. Performance tuning and the concept of algorithmic efficiency, specifically big O notation.
This part of the log is a beautiful piece of computer science. The developer details a specific structural change to boost performance. They switched the underlying mechanism the parser uses to identify whether a character is numeral or not.
Okay.
Originally, the code was using a function called element on a string.
Meaning the list of numbers was just stored as a flat line of text.
Correct. A string is just a sequential sequence of characters. But the developer updated the code to use a completely different data structure called a dataset.
Oh.
Utilizing functions called member and from list to interact with it. In technical terms, the developer notes that this shifts the search operation from O of n to O of log n.
Okay, let's break down the mechanics of what that actually means, because tossing out O of n and O of log n usually makes people's eyes glaze over.
Yeah, it sounds like math class.
But it's actually incredibly intuitive. Let's imagine we are playing a game where you have to guess a number between 1 and 1,000.
A classic problem of searching through data.
Exactly.
Yeah.
O of n, which was the old, slower method using the flat string of text, is like guessing the number by starting at 1.
Okay.
You ask, is it 1? I say no. You ask, is it 2? No. Is it 3? No. You are walking down the flat line of numbers, checking every single one sequentially.
And if the number you were looking for is 9999, you are going to be doing a massive amount of work.
So much work.
The time it takes to find the answer grows linearly with the size of the data pool. That linear growth is the n in O of n. If the list doubles in size, the worst-case search time doubles.
It's exhausting. Like flipping through a book page by page from page 1 to find the specific word.
Exactly.
But O of log n, which is the new method using the dataset structure, is entirely different. A dataset doesn't store things in a flat line. It essentially organizes the data into a branching tree.
Right.
So now we play the higher or lower guessing game.
Ah.
You don't start at 1. You guess 500, and I say lower.
And in that single second, you have just eliminated 500 incorrect options.
Half the data pool is gone instantly.
Right.
Exactly. You throw the top half away, then you take the remaining numbers, go right to the middle again, and guess 250.
And I say, higher.
Boom! You eliminate another 125 options. You make a greater than or less than decision at every branch of the tree.
So,
within just a handful of steps, you've zeroed in on your exact number out of 1,000 possibilities. That is the mechanism of O of log n. By turning a flat string into a branching tree, the search becomes exponentially faster.
if we connect this to the bigger picture, It forces us to ask why this specific, deeply technical optimization matters so much in the context of this developer's project.
Right. Why bother?
The log is actually very honest about this. The developer admits that if you were just parsing one small, single text file like one novel, the difference between scanning a flat string and navigating a branching tree probably isn't noticeable to the human eye.
Right. The modern computer does both in milliseconds.
Exactly.
So if it's so fast anyway, why do the hard work of refactoring the code? Why introduce the complexity of a data set if the user won't even notice the speed bump?
Because of what comes next. The developer states their ultimate goal for the architecture is asynchronous parsing of multiple files.
Ah, okay.
They don't just want to process one book. They want to process hundreds, maybe thousands of books all at the exact same time in the future.
It's about scale.
Precisely. I want you to consider how this applies to the systems you interact with daily, or even the workflows you manage yourself.
Right.
A tiny inefficiency like a piece of code taking an extra millisecond or a process taking an extra 2 seconds to find a file on your computer seems completely harmless in isolation.
You just shrug it off.
Exactly. But if your system scales up and your job requires you to do that inefficient action 10,000 times a minute,
suddenly that harmless little quirk compounds into a massive system-breaking bottleneck.
Right. So by moving to the faster O of log entry structure now, the developer is future-proofing the architecture.
They're doing the hard work early.
To ensure that when the system eventually scales up to handle massive asynchronous loads, the foundation won't crack under the weight of its own data checklist.
It is visionary problem solving. You have to design for the stress test long before the stress actually arrives at your doorstep.
Absolutely.
It's the difference between building a bridge for a single bicycle versus engineering that same bridge to support a fleet of freight trucks.
Right.
You can't wait until the trucks are on the bridge to realize your materials were only rated for a bike.
And returning to our earlier point, especially when those trucks are carrying the heavy, unexpected data of ancient anti-fraud numerals that an author decided to use on a whim.
Exactly. Okay, we have covered an immense amount of ground from a single specific set of developer notes. Let's briefly recap the journey we've taken through this code.
Let's do it.
We started by looking at the very structure of the workspace, learning how moving a function into a local, where clause is like giving a specialized kitchen tool its own private drawer.
Right.
We saw how the developer sacrificed a tiny bit of direct testability to prevent massive namespace pollution, choosing a pragmatic, clean system over dogmatic rules.
A triumph of organization and practical engineering.
Totally. From there, we zoomed in on the data going into that clean system, discovering the big writing characters.
The dash.
We found an ancient, visually dense financial security measure designed to stop check fraud hiding right there in the chapter headings of modern fiction novels.
Which is still just so cool to me.
It was a beautiful example of how the unpredictable nature of human culture forces rigid software to become adaptable.
The messy human element colliding with the logical machine.
Yeah. And finally, we look at how the machine actually handles that messy complexity. We saw how shifting from scanning a flat string of text to searching a branching dataset moved the system from the slow sequential slog of O of n to the lightning-fast data-having efficiency of O of log n.
Which prepared the entire architecture for massive scale.
And future stress tests.
As the developer notes in their log, it really is an exercise in software plumbing. But the plumbing determines how well the whole house functions.
So what does this all mean? When you pull back from the Haskell code, the local scopes, and the binary search trees, what is the core takeaway for you listening right now?
I think this exploration leaves us with a fascinating paradox to consider. Think about those big writing characters again.
Okay.
They were a brilliant, highly complex human invention, specifically designed to prevent human fraud in an analog world.
Right.
They relied entirely on visual density, the physical friction of the world, and the sheer difficulty of altering ink on paper without being noticed.
Because it's physical.
Exactly. But now we're building these incredibly fast O of log n digital systems that can process, parse, and categorize that dense data instantly, asynchronously, across millions of files.
Yeah.
It makes you wonder, what will the digital equivalent of big writing look like in the future?
Oh, wow.
As our systems become exponentially faster and more invisible, how will we build in that heavy, unalterable security? And more importantly, when we do engineer that ultimate digital tamper-proof system, will it be something human beings can even comprehend or read at all?
That is wow. From the heavy, ancient ink of a secure merchant ledger to the invisible, light-speed processing of modern tree structures. It really shows you that even when we are building the most perfectly logical, pristine digital systems, we are still, ultimately, just trying to safely carry the beautiful, messy weight of human culture across to the other side.
Perfectly said.
Thank you for joining us. We will see you on the next Deep Dive.